Welcome everyone. This is Bobby Harris from the Utility Broadband Alliance. As you're all getting logged in, I'm thankful to have you all on our webinar today on the 10th of September. Hoping all are doing well and safe in what they're doing. We are very fortunate today to have a great technical webinar. The tools on your dashboard as attendees, you will see a questions tool. If you have questions at the end, we'll try our best to save time to get to all of the questions. You just type those in as best you can. Remember, I'll read them word for word so that I don't butcher what you're trying to ask. So please use the questions tool to ask your questions. We'll try to get to them all. If we don't get to your question, we will follow up after the webinar offline so that we're sure that you have the answers to all of your questions. We're thankful that Nokia will be at the UBBA Summit and PlugFest in November. So you'll get the chance to talk with them in person if you're registered. We'll talk more about that at the end. But for now, I'm going to stop talking and thank Nokia, one of our Diamond members here at UBBA, one of our founding members. And I'm going to immediately turn this over to our speakers for today. We have Hanson Chan and Rob Wright, who will be our speakers. They're going to take you through this technical topic. We have 2 poll questions that we'll get to throughout so that you'll be able to answer the poll questions. So get ready for those, pay attention for those. And for now, Hanson, I'm going to turn it over to you. I have spoken clearly enough, sir. Thank you both for being on.
Thank you, Bobby. Good morning, good afternoon, good evening, wherever you are. Thank you for joining us today on this seminar on this topic of IEEE 1588. So today we would have a few, the agenda of today is we start to explore the need for utilities, with time synchronization. And then we will dive a bit into the technology of IEEE 1588. And then we will also look at a network blueprint, with different considerations that are important as you sketch out the sync network. Today utilities are operating in a very challenging and exciting landscape, right? So there are forces, from different dimensions shaping the landscape, from imperatives like net zero emissions to new innovations with grid automation technology and battery storage system, right? And also the IT technology like virtualization and AI are also finding their place in the operation landscape. At the same time, the challenges are immense, right? The utility have to provide reliable power, right, in the midst of disruptions from weather events or even cyber attacks. There are, increasing, even soaring power demand from the latest trend, which is data center and AI, right? And a lot of technology are also, evolving to more IT-like. So the tremendous, challenges ahead. So to succeed, right, utilities have to, modernize. And where do they start? Obviously, with their substations, right? So the substations need to be introduced with more digital applications, right? That's why sometimes we call these digital substations. So there are applications like from single phaser, to IEEE1588 protocols, right? For differential protection or for merging units and so on. So there are 2 things common to these applications. One is that all of them need communications. They all need networks. The second common thing is that all of them need time synchronization with a different, requirement on time accuracy. So the table here is a snapshot of what you can find in some timing challenges report from NIST and from NASB. that the link are provided at the end of the slide. You can look at those documents to have more information. But time sync, is very important, right? It's become very obvious. So what does synchronization actually mean? What is synchronization? Essentially, it means that my local clock is moving on at the same rate, or exactly together with a reference clock that can be anywhere, that can be somewhere else. In other words, local clock need to follow a reference clock without deviation. And the reference information provided by the reference clock, is multidimensional. It can include frequency, phase, and frame number, right? So depending on which element, that you follow, you are doing a different kind of synchronization. It could be frequency, phase, or time synchronization. The simplest case is, of course, my local clock does not need to know any of this reference information. This is what we call asynchronous. You don't care about the frequency, the phase, or the frame number. And then the next case is that the local clock will follow the reference clock in terms of at the same frequency, meaning that it will align with the reference clock at repeating intervals. Then the next step, the next level is phase synchronization, meaning that you don't just follow, the intervals, but you also follow the rise and fall of each interval. They are perfectly aligned, in the phase of each of these intervals. And the last one, the most challenging one, is that it follows not only the interval repeating frequency, not only the edge of the rise and fall, but also the epoch or the timestamp, right, information, right, of the reference clock. So this is what we call the time synchronization. So the question is now, the reference clock being so far away from the local clocks, how do I distribute all this information to each local clock, right, in your infrastructure, right? This is what we call synchronization distribution. So there are different technologies, right, that has been in use. So the first one is there are external sync that the local clock can obtain by directly plug into an external system. It could be a GPS receiver or a external bits clock, right? You can support frequency, phase, and time synchronization. And then the second technology that is used frequently is through the connector network interface, whether it is TDM like T1, U1, or OC3, or synchronous Ethernet, and it is limited to frequency synchronization. And the last one that on this table, on this chart, is IEEE1588, which has been receiving a lot of spotlight because of its capability to support frequency, phase, and time sync. And it is a timing over packet technology, meaning those reference information from the reference clock on the right, where you have a primary reference clock or a primary reference time clock, those reference information are transported over a packet network, to all the local clocks on the left. So now let's take a look at what it is IEEE 1588 technology. So as we now know, synchronization, particularly time sync, is important to actually many industries, right? So, and each industry have their own requirement. So I think it is fortunate that 1588 is designed to be very flexible to accommodate different requirements through what they call application profiles. So it can offer sync, for everyone, right? So of course there is a default profile, there is a telecom profile, there is of course a power utility profiles, and there are also some other profiles are optimized and designed for broadcasting, audio engineering, and even automotive. So there are different profiles. I think for today, what are most relevant to us is obviously the power profiles and the telecom profiles. Let's start with telecom profiles, right? So those are supported by many kind of telecom equipment. They could be switches or routers or optical systems or microwave equipment, right? So they support power profiles, the telecom profiles of 1588, right? So there are different options for frequency distribution only, for time and phase only, or for time, phase, and frequency, right? So I'm not going to read the information, everything that listed here. So I think it is, you can refer to that when you try to understand a bit more telecom profiles, which is important when you start to build up your sync network, especially in your core network, to distribute synchronization with 1588. So after telecom profiles, right, of course, what is really important is power profiles, because power profiles are implemented by all the grid system endpoint, whether this is a merging unit or a relay, right? So they would implement power profiles in order to satisfy, that specific need. So for power profiles, so you can see that, so there are specified in 61850 standard -3, right, that specify the accuracy required, right, and also in the IEEE IEC standard, the C37.238, that include mandatory TLV type length value, which is a specific message element for a new one specified to report the total time inaccuracy, and also for time offset that you may want to exercise when you distribute the time to the local clocks. So those are the two power profiles, for IEEE 1588. Right. So now, I would hand over the time to Rob.
Wonderful. Hanson, thank you for setting the stage for us and explaining those basics that are really important. I want to do our first poll question, and as hopefully you guys will be able to see this. There it is. Wonderful. We'll take just a moment to allow everyone to answer the polling question. How do you distribute time of day information to substations for grid applications today? As Hanson was saying, there is critical applications that require exact time of day information, and all of you have some different options there. I see people are answering the question, so I appreciate that. We'll hold just one more minute before I switch over to Rob and allow you guys all to answer that. Okay, looks like some of the answers have closed just about. All right, thank you to everyone who voted in our poll. That just helps guide us as we do more sessions in the future. So let me close that poll. And Rob, let me switch over to you, sir, so that you can take us through the remainder of the presentation.
Thank you very much, Bobby. Let me just see.
Perfect. Yes, sir. Thank you. Go for it.
And I just got to close this screen here. And this screen. Excellent. Well, thank you very much. So thanks, Hanson, for the introduction there. I mean, timing is something that is certainly looked at that's being looked at more and more in design networks. But looking at some of the basic aspects of PTP and how it's being utilized within the utility type network, when we look at what it actually is, I mean, 1588 was first published in 2008. It's a rather large document, which we're obviously not going to go into today, but it's, as we've been talking about, it defines basically the protocol for your timing distribution over your packet network. There's many options that are described. Some of them are mandatory, some of them are optional within that. But basically, you can either do it over IP or a Ethernet-based network. Now, what it comes down to is basically your peering relationship between the time transmitter clock and the time receiver clock. Now, one key point here is the actual naming for the time transmitter clock and time receiver clock have been recently renamed in the last couple of years from the previous terminology, just to be more aligned with the terms that are in use today. So you will hear me talking about the time transmitter clock and the time receiver clock. The clock identified, basically note what the previous terminology was used for that you might be more familiar with. But basically there's a peering relationship as between the time transmitter and the time receiver. Essentially messages with time stamps are sent back and forth with basically a high rate between the two clocks. Boundary clocks and transparent clocks, which we're going to talk about today, can be optionally used to help improve your network topology and your time distribution, because sometimes your networks become too large and you want to ensure the synchronized clock between both ends. Implementing the boundary clocks and transparent clocks or transparent clocks basically reduce the accumulated packet delay variation and your asymmetry, which basically will degrade the overall sync performance, which is not something that we want. So when we're using, one of the reasons why we use 1588 for your frequency synchronization is specifically for your TDM circuits, because we want to ensure that we're not going to get any slips from your head-end router down to the substation router. So we have to ensure that all along the path, the traffic is in sync. Otherwise, if we start getting out of sync from your bidirectional traffic, then you're going to start running into overruns, underruns, and slippage of traffic, which is not necessarily something you want. So one of the things that we have to also look at is it'd be nice to have a GPS located at every single hop along the path, but that's not always possible. So we have to come up with a method for distributing that time and phase information throughout the network. So basically, once the head-end router receives the GPS clock or the GNS clock, it has to distribute that clock throughout the network to ensure that everything is in sync. So let's look at some of the issues with that. One of the issues as your network becomes rather large is you run the risk of having impairments within that network that are going to impact your 1588 distribution. Some of the impairments caused by your transmission delay are going to impact the packet transfer, the delay variation, your asymmetry. So being able to accommodate or account for those and correct, in some cases, correct those impairments help to ensure your robust synchronization design in order for a correct transfer of data. So one of the ways to overcome the impairments within your network is utilizing a boundary clock. Now, like I said earlier, it would be nice if we can locate, a GPS at every single hop along the way, but that's not always possible. So by utilizing a boundary clock, we're basically breaking up this larger network into smaller segments. So we basically have the time receiver and the time transmitter basically sending that traffic down from one end to the other, breaking it up into multiple segments in order to help with a better packet delay variation control and improving your performance. So this allows your PTP to function as a valid timing option in a lot more network deployments that are starting to become rather large, where you may not be able to locate your GPS at every single site. We're going to go through some scenarios of how the networks treat where it's receiving your GPS from alternate sources, and some of the things that you can do to help improve your network design. Another option is utilizing a transparent clock, which is basically, it's not really a clock. There's no real peering relationship. It modifies the stamp and then it sends the packet through. So you do run the risk of it not obtaining the same level of performance. There is some specialized hardware and design considerations that need to be taken into account. It just becomes a lot easier with the boundary clocks because you're segmenting your network and you have a little more control over the PTP and the asymmetry, for example. So when we try and put these clocks all together in the network, we look at, obviously in a hierarchical position, we have our grandmaster clock or our centralized clock that's feeding down into the next level. Now this next level, we would utilize boundary clocks because again, now you're basically taking the time receiver and you're becoming the time transmitter to the next level. All right, so there's a little more control there. So as you're going down the level, as you're going through your network, you identify the sites that need to be the boundary clock, and then at the end, at the edge of your network where there's no further clock required, that becomes basically your endpoint. Your time receiver clock is what these sites can be identified as. Now you can, in parallel, have transparent clocks that are defined from your boundary clock down to the time receiver clock. But as your networks become meshed, as we're seeing a lot of utility networks become a lot more meshed and a lot more diversified as far as your path requirements, we look at utilizing your boundary clock in order to distribute that clock throughout your network. I think this is probably a good time, Bobby. We could probably go to our next poll question to see what kind of implementations customers are using within their networks.
I think that's a great opportunity too, Rob, for those of you who can see the screen now. We're asking, what is the current state of IEEE 1588 implementation for time synchronization at your grid? So whether you're a utility or working with utilities and you have access to this, please take a few moments and answer this question for us also.
And we do realize that this is something that we're seeing a lot more influence being put into networks, where you could no longer utilize just a frequency clock throughout the network. The demands on the edge equipment is becoming more prevalent, that you need to distribute the clock throughout your network in a more stable, robust method. And this is why we're seeing a lot more inquiries and design implementations utilizing 1588 PTP, specifically with boundary clocks.
Excellent point, Rob. Thank you for that clarification. Looks like we have had quite a lot of votes. Thank you, everyone, for voting in this second poll. We'll close off the poll, and Rob, let you go right back to your part of the presentation. Thank you, sir.
Oh, you're very welcome. So let's look at some of the blueprints. So when we look at, how does this impact your design? I mean, when we look at a hierarchical design, everything looks good on paper, but how does that actually get implemented in an actual network design? And what are some of the caveats? How are some of the management capabilities that are available to you, and some of the tools that are available to you to actually see where the sync is taking place? So we're going to go through some of that in the next few slides. I mean, as we're talking about the boundary clocks, I mean, boundary clocks are like a fundamental building block for our sync network blueprint. One of the reasons is in using the boundary clocks in that path from the grandmaster clock and the destination, the time receiver clocks. This one long path, because you look at a cloud, you have no idea where all the hops are. This one long path, like I was saying, we separate it into smaller segments, allowing a better packet delay variation control and improved timer receiver performance. This helps, as we've been talking about, with overcoming some of the impairments in the network between your grandmaster clock and the devices that are hanging off at your substation. So when you're looking at some of the blueprint considerations, we always look at from the network side, what is the resiliency? What can be done to improve the resiliency of the clock? If I lose my GPS, what are some of my options? What is the interop characteristics that are needed? We're seeing a lot more demands out at the substation for, power profile, the telecom profile, like Hansen was talking earlier. So these are things that need to be looked at as far as the interoperability or even the interworking between the different profiles. And then obviously the manageability. How do I manage the network? Do I have to go to every single node from a CLI? Or is there a centralized management option that it'll make it so much easier for me? I mean, the short answer is yes, there is an easier solution that gives you that global view. So when we talk about, all the different aspects when we're looking at what's in the announced message, there is the time transmitter clock and the time receiver clock. I mean, in between those two, there's a lot of information that gets exchanged, and the decision has to be made. If I've got multiple time transmitter clocks available to me as the receiver clock, how do I decide which one I'm going to use? This is where the best time transmitter clock algorithm, or the BTCA, comes into play. It basically is used to dynamically compare the information in that announce message that we were talking about of each of the time transmitter clocks to determine which one should I be using, which one should I be synchronizing with, and what are my options. The configured setting for the profile, when we start talking about the profile command, determines the precedence order for selecting the best time transmitter clock algorithm. So there's different characteristics that are being exchanged in the announce messages, and this is where your BTCA comes in to establish which is the best one that I should be using from my time receiver. So when we look at a few examples, when we're setting up the our topology, we have multiple nodes in our network. We have a centralized GPS. It's providing connectivity to our first node. That first node is distributing the clock throughout our network with the final destination of N3, for example. N3 is receiving sync from N2 and from N4. Now there's less hops from N2, so the BTCA evaluates the information and selects N2 because of the shorter distance. N3 recovers, so for example, if something happens with N2, then we have to be able to recover our time from somewhere else. So now N3 already has seen the clock from N2 and N4, but it picked N2. Now that N2 is no longer a valid clock source, it looks into its BTCA and says, okay, now what? Now it takes the clock from N4 because that's basically where it's going to get its clock from. That's the next option. So, I mean, this is great, but that's when you actually get a node failure. But when you start getting a link failure, what do the nodes do to ensure that the downstream nodes are no longer able to get an accurate clock from that particular node? So in this case, we're using the same example. N3 is getting its sync from N2 and N4. The BTCA evaluates the info again to select N2. That's great. What happens if our link goes down? I mean, it was really obvious when the node went down, but now that we've got a link down, N2 is still up and running, but it's no longer getting a valid clock. When it goes down, it enters into a holdover state because it can no longer obtain its valid clock, and it announces downstream that it's now in a holdover state. It still can provide sync, but it's not as resilient and valued as the sync that's available coming from N4. So now that it sees that this one has come into a holdover and is no longer valued as important or as not as valued as N4, we now N3 switches over to N4 using the results from his BTCA in order to recover the time from N4. This is all happening in the background so that the administrator doesn't need to, get a notice. The clock there's a problem with getting the clock. Now it's the administrator has to go in and modify the network. This is all happening in the background, and obviously a lot faster than how I'm clicking through these examples. But those are within the link. So another aspect that can be done, or another thing that can be done with your network, is improving the resiliency of the actual nodes that are in play. So having a node, for example, at N3, having an active standby control card helps to ensure or reduce the risk. If we lose one of the control cards at this site, we're not going to have to look for a new clock source because this node is still valid. It's still up and running off the standby. And this can also be done with redundant MDAs as well. Having that hitless redundancy is very important for ensuring the resiliency out at the edge, out at your substation. So basically, if we lose one control card, your sessions are going to continue as normal because there's really nothing being impacted within how the clock is being distributed in this network. I sat too long still. Sorry, I noticed the room just went dark. I think you can see me now. So let's look at another way to improve the resiliency within your design or within your sync. Another option is the geo-redundancy. So for example, having your GPS connected to two different nodes provides an alternate path direct to your GPS in the event of a path failure. So again, using the same design, N3 is getting its clock from N2 because it's determined that that's the best path. But what if N1 goes down? So we still have the clock that's being received from the GPS on N6, so that now becomes a valid source. So N2 is going to enter into a holdover mode because it no longer can get a valid clock from its upstream neighbor, N1, and it's going to distribute that or send down the message that I'm now in holdover. N3 is going to now look for the alternate path to get its clock source. So, oh, I went too quick. So N2 is now changed to announce that it's in holdover, and like I was saying, N3 is now, with the results from the BTCA, switched over to recover this clock from N4. This is great because your GPS is being received, it's connected into both nodes. Now, one of the things that we get asked about is, what if my GPS goes down? What if there's some jamming that takes place? Well, from a GPS topology, you wouldn't necessarily set your GPS at the same site. So N1 and N6 would not necessarily be at the same location where your GPS source is for your network design. But let's say you want to help ensure the resiliency of your clock source, so you implement a cesium clock. All right, now cesium clocks are very expensive. We have utilities that are starting to populate their networks with various cesium clocks at different parts of their network, just to help against, GPS jamming or a complete satellite failure. So basically, if this GPS goes down, we can still track the clock back to the cesium in order to ensure that our network is in sync. All right, so one of the things that we run into is the ability for, interoperating between your telecom profile and being able to provide your power profile at the edge. So this is one of the powerful advantages of the Nokia platform, is we have the ability to do this interworking between a primary PTP profile, such as the Telecom G8275 that Hanson was talking about earlier, and being able to forward that down to the substation at the edge with a power profile, either 61850 or the C37 238 version 2017. So the interworking ability of the platform helps to ensure that you can satisfy the requirements out at the edge from your fully timed network that may be using the telecom profile, which is very powerful. Rather than having a secondary box that has to be added in your network to do this interworking, it's already available within the Nokia platform that's in use in a lot of the substations out in place today. So now managing this sync. So managing the sync can be done through the CLI. There's lots of tools that can be built that are built in. You can see the different profiles that are in use, where it's getting its clock to make sure it's locked in. Just from the CLI on the particular router gives you a really nice quick snapshot as to what's going on with the 1588 clock information. But if you were looking at trying to do this at every single router in your network, that would be very time consuming and probably not very efficient. So one of the things that you could do is it can all be managed through a centralized network management platform with basically a drop-down menu. It shows you all your sync capabilities so that of each of the nodes, where they're getting their sync. So it helps the administrator get a quick snapshot of the nodes that are in sync, if there's an issue, where they're getting their sync, if it's been redirected, so that you're not left wondering what's going to happen if a particular GPS is down, you have to replace the GPS. You can all see this in a centralized management, making it a lot easier for going through sync designs and sync topology. All right, so one of the things that we are trying to emphasize is synchronization cannot be an afterthought. There is an extensive amount of sync planning that has to take place up front, identifying the different risk levels, the risk areas of your network, to ensure that your GPS or your Grandmaster clocks are locations that are going to be able to get a valid sync. Having the topology design so that you're not locating all the sync sources in one location, being able to diversify or geographically identify where they can be put within your network, helps to ensure a robust sync topology. And then also being able to manage that sync in an easy fashion so that you can look at it individually on the individual nodes, or you can see quickly from a centralized management, so that if you're doing any sync planning or you're bringing in new RTUs or SCADA systems that now require different profiles, you can see how your current network is set up in order to enable or provide the connectivity needed for the new IEDs or the RTUs that are being added at the substation, or even if you're upgrading your different existing RTUs, and now that you're needed to switch the different power profiles being available at that location. So I mean, the upfront planning is not something that can be done as an afterthought. It's something that needs to be done, along the way, or upfront from your network topology. All right, now I do invite you to, I know we've kind of gone through some of this very quickly. I do invite you to scan the QR code for more information on this topic. Like I was saying earlier, this is something that we're seeing a lot more questions, a lot more implementations taking place within the utility networks, because like I said, it's no longer just a case of adding a frequency sink. Now there's a lot more demand for ensuring the different profiles are available out at the edge for the different RTUs or the different equipment. All right, so I think that's pretty much the gist. I wanted to make sure we left room for questions or if there was clarification that was needed. I guess I'm turning it back to you, Bobby, to see if anybody is in the chat.
Wonderful. Thank you to everyone, Hanson and Rob, for that great presentation. We do have some questions beginning to come in. I will remind everyone, please use the question tool to type in your questions. I'll read them exactly as you wrote them, so remember that. So the first question that came in, and it's fairly easy, I think. What was the name of the software or application that you used to monitor IEEE synchronization between devices?
So within the network, it's our network management platform, the NSP, that has a sync topology that you can use. It's in a drop-down field in order to see the current sync setup within your managed network.
Excellent.
I think maybe I can also add that I think it is a great tool that I think Rob mentioned about, managing, a discrete set of clocks versus, a network of clocks, right? So obviously, as the infrastructure, the grid is not, a small infrastructure, there are, hundreds, if not thousands of clocks, right? So to be able to trace the direction of the flow of the clock information, to know this particular PC is using information from which upstream clock, right? So that kind of tool will give you an instant view, so you can understand how the clock flows, and even to perform some what-if analysis.
Excellent. Thank you. Another question has come in, and I'll read it straight out that is typed. In NFMP, how do you get the sync PTP topology to show up?
There should be a drop-down sync topology menu in the top, one of the top drop-down screens. If it's not visible, or if it's something that is not, that you still can't find, then you perhaps need to open up a TAC ticket, and then they can walk you through where it's located, and if there's something that needs to be enabled from the licensing point of view in order for you to have that.
Excellent, thank you. Yeah, we don't have a live screen that we can take you through, but thank you for answering it. That was a perfect answer. Thank you. Okay, I'm going to keep reading. Good questions coming in. Does that network management software work with any cellular router or only Nokia routers? And the second half of the question is, if any, what standards does the device need to support, or is it just GPP or something else?
So this is based on the management of the Nokia routers. So obviously the network management software that's managing the Nokia routers, the NSP is what we're talking about for having that ability to see the sync that's within the Nokia routers that it's currently managing. To my knowledge, it does not manage or have the ability to see the sync on other platforms. I've never tried to use it on other platforms, but I can't see how that it would work, because you would need to have the ability for the management component, not just being able to see traps and alarms through your MIBs, but you would actually have to be managing the device, and that's probably focused more on the Nokia routers.
Excellent. Thank you. All right, the next one. On the telecom side, does leased transport connectivity versus company-owned transport pose any challenges when trying to synchronize time between nodes? I can reread that if I need to.
Nope, that's a good question. I mean, it does come down to the type of transport. I mean, we run into this quite a bit, not necessarily between, your company network, but depending on the transport between your nodes can help determine what is available for you in order to distribute your clock. So in Hanson's slide, he was showing the different methods for distributing your clock. One of them was, frequency sync, or Sync-E, sorry. Sync-E is not always available depending on the type of transport that you have. One of the reasons why customers go with 1588 PTP for distributing it is because it's a packet-based. So it generally will work even when a Sync-E will not work because the underlying transport does not support it. Because it's packet-based, I mean, you do have the ability to adjust the levels of quality of service within the network, but it would be the same as sending packets over a network. If you don't have the ability to send packets over a network, then you're not going to get your sync over it, but you're also going to have a bigger issue because you're not going to have your data traffic transmitted over that path as well. So it does really come down to, the transport equipment along your path and what it supports. And some of the things I would recommend looking at in the transport path, whether you have fiber optics, whether you have microwave networks, the versions of the microwave networks, patch panels, these all come into play when you're looking at how the clock is being distributed. And one final note, our routers will actually identify if the clock being received is qualified for use. So you can actually see the tools that are built into the platforms will help you to establish if the clock that is being received is qualified for use, or if it's just not good enough in order to be classed as a primary clock for the network.
Maybe I can also add, some more color, to Rob's, answer, right, and information from Rob. So I think the question also mentioned about leased versus company-owned, right? I think for leased lines, right, I understand that there are some providers that are more at the forefront. They're even thinking about offering sync as a service over their network. So so it really depends on which carrier you are working with, the lease infrastructure that you are using, right? Whether they also support that kind of sync as a service, products, right? So there are possibilities, right? So I think sync itself, right, is sometimes it works like a black magic, right? So it takes you need to really fine tune your all the configuration, right, to make it work.
Excellent. Yeah, that was great to add. Next question. How can 5G ultra low latency be used for timing and work with IEEE 1588 V2?
So that's an interesting question. I think that's a little beyond the TDM requirements that we're talking about in this network. And I think it's probably a little early to establish the 5G impact on the sync as far as distributing your clock through a 5G cellular network versus the fixed wired network. I don't know, Hanson, if you've had any insight into the 5G aspect of this.
I think the question would probably come from the need to distribute sync in a field area network, right? In a fan, right? Yeah, I think I agree with Rob that that a lot of research work is still ongoing on this topic, right? So I don't think he has become something like a standard way or figure out what is the well-proven recipe, right, to do that.
Excellent point. Excellent. Thank you. So perhaps help us understand how BTCA, or best times transmitter clock algorithm, makes the selection for which upstream clock source to use. If you can explain that a little bit.
That was very good, and you did well on the new terminology, Bobby. I will give you credit on that one. I myself am still getting used to some of the new terminology, and I do find myself catching myself because you've used the same terminology for years, and now you just have to retrain. I mean, everybody has to retrain their thinking. So I mean, there are multiple criteria that are used for the best time transmitter clock algorithm selection. I mean, this is something, it's like kind of it often appears like a black box, like Hansen has referred to, with no visibility. We do recognize the challenge in identifying the different selection criteria, and we are actually adding a feature within our platforms to display the parameters in the best time transmitter clock algorithm selection criteria. So like I was saying earlier, I mean, this sync has always been in the networks, but it's really been very limited as the requirements. So now that there is more demand and more requirements for the understanding of, what sync is available, how do I distribute the sync, what criteria is being used for that selection, we're constantly updating and adding new tools to help improve the ability to see where some of these, exposing that black box visibility in the selection criteria.
Wonderful. Thank you for explaining that. So you talked a bit about boundary clock and transparent clock. When would you use boundary clock versus transparent clock?
So that's a good question. And we hear, we've talked about the boundary clock, and that's been primarily one that we've done for a lot of our designs. And some of the reason for that is the ability to ensure that consistent clock by segmenting up or basically breaking up the larger networks so that they would appear as, smaller segments to ensure the packet delay variation. I mean, which is the best one? It will definitely depend on the network design requirements and basically your nodal architecture. So our recommendation is to use the boundary clocks because of the clock benefits that we're talking about today.
Maybe I can also add a bit more, another dimension to Rob's, question, answer. I think, using a boundary clock, right? As we said earlier, right, as Rob said earlier, transparent clock is not actually a clock, right? So the node, the communication network node that implement the transparent clock have no information, no idea what is the timestamp information being passed along. He has no idea about what is the timestamp, right? So it would look like the telecom layer is operating in a different time domain as your electrical layer, right? So with boundary clock, right? So that is, the telecom node can actually receive the clock information from the upstream time transmitter, right? And get the timestamp, generate a timing information, the time information for its own use, so that the telecom node is actually using the same time source as your electrical layer, right? So that means your telecom layer, network layer, and your electrical layer are all synchronized. I think to me it is a great benefit that can help utilities operation to align a lot of events. in terms of when you try to reconstruct, what happened during a network or failure, network being both telecom network and your grid network, right? So you can now synchronize all the events from your telecom nodes as well as your IEDs, right, in your substations, and then have a fuller picture, right, to do post-mortem analysis.
Excellent. Excellent, Hanson. Thank you for adding that. So we did some polls, but I guess the last question that I'll ask is, so if I need to start a sync network design, where should I begin? What suggestions would you have for someone who hasn't done this yet?
So that's a very good question. In a lot of cases, it comes down to looking at your topology, understanding the topology that you have available to you and where you can locate your clocks. So you don't want to have too many hops away from your clock source, but for your time receiver, but you also want to ensure you're covered in the event of a network reroute, for example. So it has to be some consideration done for your optimized path and alternate paths, and where clocks need to be present. You also have to establish what type of risk level do you have, which will determine the number of clocks that you put in your network, but also adding cesium clocks. If the risk of a GPS failure or loss of satellite communication is high and you don't want to chance it, adding some cesium clocks maybe in your network is an option that you may want to consider. So definitely the topology is one of the big things that need to be considered in any sync topology network design, because you also have to look at the intermediate transport in your network to establish what kind of distribution of time, what kind of method can I use to distribute my time through the network. Is there a lot of fiber patch panels? Is there a lot of older microwaves? I mean, these are things that will impact what type of clock or what type of distribution method can be used in order to distribute the clock around your network. Could you be using a hybrid approach? Absolutely. Well, we have lots of networks that are using Sync-E, for example, in parts of their network, and 1588 in other parts of their network. And we have some networks that are still using ACR, adaptive clock recovery, in some of their networks. It just depends on what is available, what makes the most sense, because the ultimate goal is to ensure the synchronization between the endpoints. And then when you get into the redundancy of your network, there's different design considerations that can be done to help ensure the redundant path for your data can be achieved from your primary location or your head-end location down to the substation, as well as not just redundancy for your sync, but redundancy for your data side.
Excellent.
I think maybe I can also add some spice to the food, to the dish. I think like sync design, I think is quite a large and broad topic, right? So I think Rob had laid out for us, what are the variables, what are the things to consider, right? I think to me, I think it's fortunate that, I think in Nokia, we do have a team of very experienced network designer that has experience working with utilities, right? And with sync design, I think they will be happy, right, to work with, with you, right, with utilities, right, to get a grip on the network design based on your particular, network asset mix, right, and your requirement, right, to work together some, sync blueprint that you can move forward.
Excellent. And we certainly will continue this conversation at the UBBA Summit and Plugfest the first week of November. For those of you on the call who have not yet registered, go out to ubbaplugfest.org and find all of the agenda, get your registration and your hotel booked. Hanson and Rob, thank you so much. This was really a top, interesting topic. I appreciate you breaking it down for us, answering everyone's questions. It's just been terrific. So thank you to everyone who joined us today. Thank you to Nokia. Thank you again, Rob and Hanson. And we will see you all in Kansas City the first week of November. And we'll be back with another UVVA webinar again soon. Thank you.
Thank you very much,
Thank you.
Bobby.
Thank you. Until next time.